There we go. All right. So recording's working this time. So what I'm going to do, I'm going to recap section 4.1. We'll go into 4.2. Hopefully we'll get through 4.3. So just to take a look at 4.1 again. What we're going to be doing in chapter 4, we're going to be looking at derivatives as a tool to learn something about functions. And we're going to try to learn things about functions that were kind of hard to figure out in algebra. So mainly we're interested in minimums and maximums. So if we have, say, like a function doing something like this, we might call this a maximum. And this would be a minimum. Or basically, for this part of this function, this section of it, highest value of this function, smallest value of this function, or lowest value. So that's what we're going to be looking for. And this is something that's going to really consume our interest, at least through section 4.4. And we're going to slowly develop tools that let us find these minimums and maximums and come up with properties of functions that we could kind of hint at in algebra, but we're going to actually get a little bit, hone in a little bit better. So for example, like in algebra, what we would typically do if we have f of x is continuous. And we might figure out that let's say on AB, we know our function does something like this. And we have zeros at A and B. Or in other words, so what we would do at this point is we would pretty much assume, given that f is continuous, that means there's no gaps or jumps or anything peculiar like that. This function f of x, if it's crossing here and crossing here, then it has to have some kind of behavior like this. And another way of saying this is that somewhere between A and B, f of x has a maximum. So this is how we handle maximums and likewise minimums in algebra. And that's about as good as we could do. We didn't actually try to find the value of x where this maximum occurs. We just sort of say, well, if the function's doing this and it's doing this because we have zeros at A and 0 at B, the function has to be doing something like this if it's continuous. What exactly this looks like, we're not sure. So what we're going to be doing, we're going to be in these next 4 sections, is we're going to be trying to figure out how to identify these max and minimums Well, exactly. Where does the max actually happen? And where does the minimum actually happen? So let's recap some ideas from section 4.1. We can have an absolute max. And this is the maximum of f of x on its domain. So we have an absolute max of f of x. What that means is the maximum of f of x on its entire domain. So all x-axis. So an example is something like that. Let's say f of x equals negative x minus 2 squared plus 4. Double check that real quick. Let's go plus 2. All right. So what happens if we graph this? Quite as high. So we have this flipped over parabola. This is the highest point, 2, 2, on this graph. And then it goes on and on forever down like that. So this would be an absolute max. And I'm just going to mention the domain is negative infinity. Now, sometimes your domain might not be something like this. It might be something that's a subset of this. And you could still talk about an absolute max, because on that entire domain, if you have your highest point, that highest point would be the absolute max. So a more formal way of expressing this let me see, make sure it's if. And there's that key word again. Let's squeeze it in there. Squeeze it here. For the domain. So f of x is less than or equal to f of c, where if at x equals c, that's where we have our max. So in this case, 2 would be our c. So questions about that? All right. Likewise, the absolute minimum, this is going to be our smallest our smallest value of f of x on the domain. That's where we find our minimum. And then we have a formal way of expressing this. Well, here, I'll do a picture. Take f of x equals x squared. And the absolute minimum. Take a look at this function. On the domain. So again, it's that lowest point, or that sort of smallest point, I guess you could say, that's going to be on our graph. And again, we have a formal way of expressing this. Again, absolute. We're talking about domain. Now, there is sort of another version of this. You will see the term absolute used in a particular situation when we're talking about intervals. So when we talk about the absolute minimum or the absolute max, we're assuming we're talking about the entire domain of this function, and that could be the entire x-axis. But we could also be a little specific here. We could have an absolute maximum on a closed interval AB. And what this is going to be is the largest value of f of x on AB. So we can take this idea of absolute max and we can shrink it down just to an interval. So what that might look like. So if that's our f of x, got a c in there, f of c, c comma f of c is our absolute max on A. So in this case, we're not talking the entire domain. We're just interested in what's going on in this interval. And again, there's a formal way of putting this. Again, we're limiting ourselves to the domain. So that's what we talk about. That's what we mean by an absolute max on AV. And when we talk about an absolute minimum, well, it's going to be the same idea. And for this, we'll have the smallest value f of x on AV. So that's our absolute minimum. So again, just a little pictorial example. So here at C, f of C, we have an absolute min. A and B. And again, there's a formal definition for this. And so there we go. So questions about that? All right. Now, this is a little bit different from when they talk about local minimum and local maximum. So local minimum and local maximum, we're being a little more flexible, at least flexible on one thing. And it has to do with the kind of interval we're working with. So local maximum this is the largest value of f of x. And we need to be a little specific. Largest value of f of x near x equals c on some open interval AB containing C. So we're talking about local max and local min. We're just basically saying if we're kind of close to x equals c, well, f of c is going to be bigger than all the nearby points. That's all we're saying. It's really not too different from what we're doing with the closed interval, though there is a difference, and we'll talk about that in a bit. So what this might look like. There's A, there's B. They'll look pretty much the same. Oh, sorry, wrong one. So we're looking for something that looks like this. And it doesn't look any different from when we worked with the absolute maximum on a closed interval. In this case, we're just working with an open interval, but it is going to be significant. And again, we'll talk about this, the difference between working with local versus absolutes within our intervals. And again, there's a formal definition. So f of x is less than or equal to f of c for all x in AB. And again, open interval instead of closed. So that's local max. Again, we're going to have a local min. Kind of seeing a pattern here. So local minimum, again, smallest f of x at some x equals c on an open interval that contains c. So again, it's going to look very similar to our closed interval. So this would be our local minimum. Or another way of putting it, f of x is greater than or equal to f of c for all x in this open interval AB. So questions about that? So basically, when we talk about min and max, it depends on what we're focusing on. So give me a second to write that down. We could ask about the minimum and maximums of a function over the entire domain. We could ask about the minimums and maximums on the closed interval. and we can ask about the minimums and maximums on an open interval. Well, we could kind of see a difference between domain and closed interval because the entire domain could have some pretty wild minimums and maximums, and then in a closed interval, things might be not as wild, I suppose. And you'd say the same thing about an open interval. But there's a big difference between the open interval and the closed interval. So just to summarize what we have so far. Absolute, min-max. This is the domain. And then we have absolute, min-max on AB. So this is the min-max on AB. And then we have local. And that's going to be it. So this is sort of a summarize what we've just looked at. Now, how are these two going to be different? And it's going to come down to endpoints. When we talk about minimums and maximums, we might have a situation where some functions don't have a minimum or maximum. And that can be kind of peculiar. So for something like this, let's say we're looking at absolute min and absolute max. So let's take a look at this when there's no minimum or maximum. So let's say f of x is x squared on its domain. So we're going to look at the entire domain of x squared. Well, since we're looking at the entire domain, we're going to be talking about absolute max and absolute min. So this is what we're looking at. So if we take a look at this, here, a little bit off the drawing. Here we have an absolute min. But there actually is no absolute max. This will just go on forever, and this will go on forever. So there's no value of f of x that's bigger than all the rest. So in this case, there's no absolute max. So you can actually have a situation where you don't have an absolute max, but we do have an absolute min. This is the smallest f of x we'll get. So that's one way you can have a situation where there's no max or min. Now another one is this. Look at x squared on negative 1 and 1. Now, this is an open interval. So that means we're talking about a local max and min. So that means we'll have holes at negative 1 and 1. There's here. So once again, we do have a minimum. And so this is going to be a local minimum. Here, I'll put the parenthesis in the parenthesis here. But once again, we're not going to find a largest value of f of x on this interval. Because it's an open interval, any value of f of x you pick that's less than 1, you can always find one between 1 and whatever point that you picked. So what this means, there is no largest value of f of x on this open interval. So that means no local max. Ooh, this is really lopsided. Let me fix this. Better. So what it means is this. If you travel along this curve, you can't ever get to the point 1 and negative 1. But you can get infinitely closer. And there's always going to be some point between where you are on this curve and this point where you can't go. There's always a little point farther along. And when you think you found the closest you can get to this open point, turns out you can always get a little closer. Take the distance between you and this open point and cut it in half. Then we zoom into this, cut that distance in half. Zoom in, cut that distance in half. You can always get closer. So that means there's never an actual point where once you stand here, the only step left is to fall into that hole. You can always get a nanometer, picometer closer. So that means you never actually find a closest point to that hole. That means you never find a maximum for this function. So it has no local max. So that's why local extrema may or may not exist, or one example of it. So I skipped over one, the closed interval. This one's special. And this brings us to the extreme value theorem. So if f of x is continuous on this closed interval AB, so now we're switching our domain, we're switching our focus. We're not talking domain, we're not talking open intervals, talking closed intervals. So f is continuous on closed interval AB, f of x has an absolute min and max on AB. this is always going to happen. So, well, yeah, as for continuous, that is the thing. As long as f is continuous, this is always going to happen. I mean, you can come up with functions and you can look on some interval AB, like say a function that has a vertical asymptote inside AB. But if the function's got a vertical asymptote, it's not continuous at that location of the asymptote. So the asymptote example wouldn't count. We need f of x to be continuous on AB. So no asymptotes, no gaps, no jumps, nothing like that. It's just going to be smooth and connected through no holes. So as long as f of x is continuous, you will always have an absolute minimum and an absolute maximum on AB. So to give an example of what this could look like. Sort of an imaginative example. So again, we could have a function do something like this. We have our max, and we have our min. All right. So there we go. We can do something like this. Well, I mean, you can have this on the open interval too. This could have been a local max and a local min if these were open. But here's where the difference is going to come up. Let's go back to this example. Take a look at this one. Ah. So do that again. Me having trouble with parabolas today. There we go. So once again, we have a minimum. But because these are closed intervals, we can get to these points. So that means we have two maxes, not just one, but we have maximums at the endpoints. So that's something that closed intervals allow us to have. We might not be looking for our minimum and maximums between A and B. They could occur at the endpoints. So this is what's powerful about this closed interval. We could have a min and max occurring at the endpoints. So if we don't find a min or max in between those endpoints, we can look to the sides, and that might be where the min and max are. Oh. So to find the minimum and maximum of a function on AB, oh, let me do one last thing to recap critical points. So when we talk about critical points, this is going to help us find the minimum and the maximum. This is the big difference with algebra. So computing the value of f of x at the endpoints, that's not too difficult. We can do that. But how do we find whether or not f of x has a minimum or a maximum between a and b? That was the big issue with algebra. Well, this is what we're going to do. First off, what are critical points? X equals c is a critical point if the derivative of f at c is 0, or the derivative of f at c is undefined. Those are critical points. So how is this going to help us find out if f has a minimum or a maximum somewhere between the endpoints, at the interior points? Well, let's take a look at something. Note. Let's say f prime of c equals 0. What does this mean? Well, it means the slope of the tangent line to f at this point x equals c is 0. That means the tangent line is horizontal. I'm going too fast with the erasing, let me know. So what this will look like it's going to be this. So what that means there is a max or a min at x equals c. Here, let me draw the minimum version of this. So what we're going to come up with is a theorem that says this. If, oh, let me do one thing. If f has Let me double check this. Okay, good. If f of x has a local minimum or max at x equals c. So we're not worried about endpoints in this case. We just want to get close to c. So we can work with an open interval if we want. Just want to be close to c. And f prime of x exists at x equals c, then f prime of c is equal to 0. So when we have the derivative existing at the points throughout our interval, and we take that derivative and we set it equal to 0 and solve for x, that's going to tell us what c is. It's a way we can identify the maximum or the minimum of a function, where along the x-axis it occurs, and that was something we couldn't do in algebra. Now, the other thing it mentioned about critical points is where the derivative is undefined. So in this case, we might have something like this. If you recall, when we have a cusp like this, that means the derivative is undefined. So we could have a situation where we might have a maximum or a minimum, and the way we can find that point is we want to look where the derivative is undefined, and we want to test that point also. So now it might not turn out to be a minimum or a max compared to what's going on with f of x in other locations, but it is a point we're going to be interested in. So to summarize what this is doing, what we're going to be mostly doing is focusing on closed intervals. And so this is how we're going to do that. We're finding minimums and maximums on A column B. So what are we going to do? Well, what we want to do, and we're going to test f of x at endpoints. X equals A and x equals B. So we want to find the value of f of x at those endpoints. Then we want to test critical points found in the open interval AB. So this is something we can do that we couldn't do in algebra. We can use the derivative to discover critical points, where the derivative of f equals 0 and where the derivative of f is undefined. So let's take a look at an example. let's see here. So let's say we have this. And again, we're working on these closed intervals, -1 and 1. So what we're guaranteed, if we go back to the extreme value theorem, because we're looking for a minimum and a maximum on a closed interval, we're guaranteed to have them. We just got to find out where. So first off, endpoints. And, oh, shoot. Let me change this up. Let's go 0 and 4. It's getting my functions mixed up. Let's go 0 to 4 on this. So that's what we're going to test. X equals 0, X equals 4. And take a second to update your nodes. We're not going to do -1 to 1, we're going to do 0 and 4. So f of x, let's take a look at f of 0. It's -0 minus 2 squared plus 4. And if you hammer that out, you're going to get 0. So f of 0 is 0. Now we look at f of 4. And if you hammer that out, you're going to get 0. So at the endpoints, f of x is going to be 0. So let's take a look for critical points. So for critical points, we want to take the derivative of f. So we get -2x minus 2 plus 0, or -2x, 2 times x minus 2, or -2x plus 4. And we want to set that equal to 0. So first off, if we take a look at f prime of x, this is f prime of x. There's no way that's going to become undefined. There's no division by 0. There's no square roots of x. There's no natural logarithms or logarithms. There's no trig functions that have domains that don't allow certain values of x. For our derivative, all values of x will work. So we're not going to worry about undefined. But let's find out where this is equal to 0. If you solve for x, look at x is 2. So for the endpoints, they gave those to us. It's 0 and 4. Those are the endpoints. The critical point we had to discover. And just like we look at the value of f at the endpoints, we want to look at the value of f at the critical point. So f of 2 and we're going to get 4. I might have graphed this function wrong. I'm realizing. I apologize if I did. I might have graphed it wrong. When I did the graph, it's a little higher. So we have equal to 4. And what does this tell us? Well, let's take a look at what we've discovered. For the endpoints, we have this. So what we come to realize, our minimum or maximums, they're going to happen at these locations. So what we get is this. We have minimums, and this is going to be x equals 0 and x equals 4, and then a max and x equals 2. And so that's where we locate them. So the minimum itself, in fact, let me put this in more appropriate terminology. We have an absolute minimum on 0, 4, and again, closed interval at x equals 0 and x equals 4. And then we have an absolute max on 0, 4 at x equals 2. And so these would be our answers. So when we look for these absolute minimums and maximums, what we're going to do is look at the endpoints, and then we're going to look at the critical points, where the derivative is equal to 0, or where the derivative might not exist. All right, let's see here. So that's pretty much it for 4.1, and I guess I really did a lot more in there than I was expecting. So let me try to at least move on to 4.2. Maybe we don't get 4.3 today. But 4.1, there's a lot of terminology. It's a good foundational section where we want to make sure that everything's okay. We want to make sure everything's solid. All right. So just looking at 4.2, there's basically two ideas in 4.2 we're going to look at. And the first one is Rolle's theorem. And what it says is this. If f of x is continuous on a closed interval, again, we're emphasizing these closed intervals. So if it's continuous on a closed interval, according to our extreme value theorem, we're going to have a maximum and a minimum for f of x on this interval. So f of x is continuous on AB, and f of x is differentiable on the open interval AB, then if f of A equals f of B, then there's, let's see, a point for an x equals c in this open interval. So there's some c between A and B where f prime of c is equal to 0. So this is actually the same idea from algebra. What it's basically saying, if you think about it in terms of algebra, you think of zeros. So a function crosses the x-axis, comes around and crosses the x-axis again. as long as f of x is continuous, then somewhere between those two zeros, there must be some maximum to this function. So that's basically what Rolle's theorem is saying. So if we have some line y equals b, we have a function doing something like this. Call this A, and we'll call this capital B. So here we have f of A equals f of B, which is going to be this capital B. Then what this says, there's a C where f prime of C is 0. Or in other words, you have a horizontal tangent line. And again, that tells us if we have a maximum or a minimum. So if we have a maximum or minimum, then we're going to have this condition where f prime of C is 0, as long as the derivative exists at that point. So questions about that? Let me do an example here. So let's say we have this. We'll bring back this function. So let's take a look at this. F of 1 equals minus 1 minus 2 squared plus 4. Or, let me do my arithmetic, it's going to be equal to 3. And then f of 3 minus 1 minus 2 squared plus 4. And, oh, sorry, it's going to be 3. And that's also going to be equal to 3. So what we get is f of 1 equals f of 3 is equal to 3. So that means because f is continuous, and that function is continuous, there's no division by zeros, no square roots, no natural logs or secant functions that we have to be concerned of. So the domain, so f of x, is continuous on 1, 3. And also, f is differentiable. Abbreviate differentiable on the interior points. Because if we recall what the derivative was, f prime of x was negative 2x plus 4. Is defined on all points in 1, 3. Say all x, not points. How do we do it? Okay. So it's continuous. The derivative is going to exist at all the points. So that means by Rolle's theorem, there is an x equals c in 1, 3, where f prime of c is equal to 0. So that's all that Rolle's theorem is saying. And again, from the last section, define that point, that c. F prime of x, and we did this already. We just set the derivative equal to 0. We'll get negative 2x. Here's negative 4. And x equals 2, which is going to be RC, which is what we found last time. So questions about that? So that's how we use Rolle's theorem. It's really just to tell us that this thing has a maximum or a minimum if f of a equals f of b and the function is continuous and it's differentiable. Well, it's not just a max or the minimum. What it really is telling us is that there's a number between a and b where this will have a derivative that's equal to 0 if, again, f is continuous on that closed interval and it's differentiable on the open interval. And that means we have a derivative that has a value of 0 somewhere in there, or a value of x that lets that happen. So that's Rolle's. So what this does, this sets us up for the mean value theorem. And what the mean value theorem says is this. If f of x is continuous on closed interval again, a and b, and differentiable, I'll abbreviate this just for the sake of time, on the interior, refer to the open interval as the interior of the closed interval, still using those same endpoints. Then there is an x equals c in this interior where f of b minus f of a over b minus a equals f prime of c. So again, we want f of x to be continuous, no holes, no gaps, no jumps. We want it differentiable at all the points, at least on the inside. So we're not talking about any cusp or anything like that. And if those conditions are met, this happens. So what is this actually saying? Well, what it's saying is, let's say we have a function doing something like this. Here's A, here's B. And we have our f of a. So what we're doing here is we're calculating the slope of a line that's passing through these 2 points. Let's see, my drawing skills have been a little bit, well, as I like to say, artistic license. So this here is the slope of a line passing through this point and this point. And what the mean value theorem is this. There's going to be a point where a tangent line a point on this curve where there's a tangent line that has the same slope as this line passing from here to here. That's what this is saying. So the tangent line at x equals c has the same slope as the line passing through AF of A and might be a little hard to see. Let me know if you have a hard time seeing this. BF of B. This is a little small. Please let me know. We're here, just to make sure. To get you much closer, I'll try. About 10 more seconds. Then we'll do an example, and then that's going to be it for today. All right. Here comes the challenge, re-establishing that. There. So let me do an example of how this works. And that'll be it for today. And I'll get us through 4.2, which isn't bad. 4.3, we could do that when we come back. It's kind of fast. So let's say we have this. Let's see. So let's say we have f of x equals x squared 0, 2. So what we're going to do is this. Mean value theorem says this is what it says. So that being the case, now we can say this again because f of x is going to be continuous on this closed interval. If we take the derivative of this, well, we'll get the derivative f prime of 2x. F prime of x is 2x. So this is going to exist on, well, any number from that interval. There's no division by zeros that could happen here. There's no square roots. Again, no logarithms or secant functions we need to worry about. So this is going to work. So what do? Well, what it says is this. For us, a will be 0, and b is going to be 2. So we have f of 2 minus f of 0 over 2 minus 0. Well, f of 2 is 2 squared, or 4. F of 0 is 0 squared, or 0. And we have 2 minus 0, or 4 over 2, 2. So that's the slope of the line passing through points on this function at x equals 0 and x is 2. So draw a picture of what this is. A little more. We're talking about a line passing through here. This line has a slope of 2. So what we're going to claim is this. There's a tangent line, according to the mean value theorem, there's an x equals c in the open interval 0 and 2, where f prime of c also equals 2. So we have to find the c. So to do that, f prime of x is equal to 2x. And so we're going to set f prime of x equal to 2x. We're going to set it equal. Oh, let me write it out since it look like I'm doing a computation. Set f prime of x equal to 2 and solve for x. So this is the slope that we just found. We computed f prime of x, that's 2x. So this tells us x is equal to 1. So what this is saying that this line passing through like this has a slope of 2. Well, the tangent line sorry, artistic license. Different pen. The tangent line, it's tangent to this curve at x is 1, would have the same slope as well. It has the same slope. Yeah, let me zoom you in for that one too. It's a day of zooming in. I'm going to move on in about 10 seconds. All right. All right. So real quick, just one little corollary to add to this, and then that's it for today. If f prime of x equals 0 on the open interval AB, then f of x equals c for all x in a comma. So again, we're using the idea that a derivative means a slope of, when the derivative is 0, the slope of your tangent is 0. And the slope of a tangent being 0, well, that means your tangent is a horizontal line, a constant line. And so what that is giving you is if your derivative is 0 on an open interval, that means for f along that open interval, you're going to have horizontal tangent lines. And so that means on the open interval, f is a constant function. So that's it for today. It was really a big rehash of 4.1, and we did some things with 4.2. We looked at Rolle's theorem and the mean value theorem. And you have some interesting homeworks to work on, some good examples. But that was something that probably not a bad idea to really nail down the ideas of 4.1. They can kind of swim around a little bit if you're not careful. So we'll do that. I'm going to record 3.11. I think that's just a section I want to spend some time on, make sure that's clear what we're doing in there. And then I'll post that as well. And if any questions, let me know. And keep in mind, I think I just caught it, that graph, that parabola. And I'll send out a note to everybody just in case someone missed it. This, you might want to adjust it in your notes. It does have a max of 4 at x equals 2. But I'll send something out about that. So that's it for today. Get any questions, let me know. You've got your quiz turned in for quiz 2. Don't forget the take-home quiz, quiz number 3. That's due on Friday. And I'm going to adjust the homework here so you have time to work on them. And other than that, that's it. If I think of anything with spring break, anything you just might want some review or something like that, I'll let you know. Other than that, have a wonderful day. Have a wonderful spring break, and I'll see you soon.
Thank you, Professor.